All right, so officially welcome everyone and welcome to our speaker. It's my pleasure to introduce today Jürgen. I won't say your last name, it's even harder than mine. It's written. Let me introduce Jürgen first. He studied at the TU in Munich and at the MPE in Garching, and then moved to EIP in Paris and subsequently to IRAP in Toulouse, where he's still today. He's a NRS staff scientist since 2001 already. And he's worked in the field of gamma ray astronomy and data analysis and instrumentation on the topics on nucleosynthesis and antimatter, followed by Fermi and more recently CTA and the topics of cosmic ray physics. He chaired the CTA consortium for 9 years, but recently he decided to step down and focus on his new passion, which is our passion, sustainability issues in astronomy. Jürgen recently completed a training on carbon footprint analysis, and he's going to tell us more about this today. So Jürgen, I'll leave you the floor.
Okay, thank you very much. So I'm really happy to present this work to you. I mean, this is basically the summary of a paper which is in press now. I mean, it's already on arXiv and it will come out in Nature Astronomy in the next weeks. I don't know exactly when. And this is a work we did together with a group here at IRAP in the context of the assessment of the footprint of our laboratory. And as it was just mentioned, we did all a training for our carbon footprint estimates in 2020. It was in fact perfectly matching with the first COVID lockdown. So we did this remotely, and it was a very interesting training. So I just can recommend to everyone to do these kind of things. And our ambition at IRAP was to make a full scope analysis of our footprint, including basically really everything. And so going a little bit beyond beyond estimates that other labs have done in the past in the astronomy domain. And this shows here, this slide here shows the outcome of that, the camembert, how we call this in French, the pie chart. And interestingly, what you have here, I mean, this orange and these red boxes, this is the use of data from research infrastructures, and I will talk about this. And this is the dominant part of our footprint. Another important part is here, this greenish pie, which is all the purchases that we do in our lab. And when you add the purchases and the instruments that we use, we will have almost already 80% of our footprint. And these were typically things that were not on the radar of other footprint estimates in the past. So it's really important to take these into account. So when I talk here about research infrastructures, what I'm meaning is basically all our telescopes that we use, including, well, space telescopes, but also space probes. Specifically, we use them here at IRAP in plasma physics or planetary physics, and also ground-based observatories. So you may, of course, wonder, why should astronomers consider this footprint? Well, without astronomical research infrastructures, it's pretty obvious that astronomy wouldn't be possible. And when you think about these carbon footprint estimation method that we used, what they call here bilan carbon, they basically say, well, to identify what you have to take into account into a footprint estimate, just ask yourself the question, will your activity be impacted if you remove a given flux, input or output flux, to your enterprise or organization? And of course, if you remove, as I just said, research infrastructures, there won't be any astronomy anymore. But even further, I mean, also astronomers have some responsibility, because first of all, the telescopes we use are essentially invented by the astronomers, and they contribute to building and operating them. So also they share the responsibility there. And also without astronomers, there won't be any astronomical research infrastructures at all. So, we started to look into that, and the method we employed is just a basic method of estimating a carbon footprint. So you define the boundaries of your analysis, and we started off with all the infrastructures used by our lab in 2019. That was the reference year for our analysis. We included all kinds of emissions, so a scope 1 to 3 analysis, and in terms of time frame, we included construction, launch, and operations. And then you need activity data and emission factors. And as activity data, we just use an economic input-output analysis, meaning we use basically mission cost, but we also use payload weight and for ground-based observatories, construction and operating costs. And then we need, of course, emission factors. They say basically how much CO2 you emit per amount of money spent or per weight of your payload. And just importantly, I mean, the boundary goals that we set here, they were not always met. So formally, our analysis results are only lower limits to the truth. Now, the one important ingredient is the emission factors. And to estimate those, we looked basically into existing carbon footprint estimates for space missions or ground-based observatories. There aren't many. I mean, they're really very scarce. So, I mean, this is, of course, a bit at the critical point here, but I think we made quite solid estimates here, at least not estimates that are overestimates, but maybe rather even underestimates. So we tried in this whole analysis to be conservative, to not overstate the footprint somehow of these infrastructures. So these are the numbers we came up with. And when you compare these numbers to numbers for other activity sectors, and I wrote down a bunch of numbers here, you see, in fact, that these numbers are really on the low side. And which means then also it will be quite challenging to decarbonize our activity sector, because it's really just hard to make these numbers even lower. So the next thing, and this was in fact the most time-consuming part of this work, was collecting activity data, and mainly collecting, in fact, cost data. I mean, not many observatories or space missions make cost data public. So sometimes you really have to hunt them down in literature, or you have to even extrapolate values from documents that you can find for national contributions and so on. So of course there's some uncertainty in here, but we used also the second approach for space missions that we base on the mass, in fact, of the payload or the satellite, and here the collection of mass data is in fact pretty easy. We find them everywhere, and nobody makes a secret about them. But sometimes for the cost estimates, we couldn't find data, and specifically for mission extensions. It was, I mean, very often they are not included in our analysis. And also for ground-based observatories, we never included upgrades, which means that also here, I mean, that our results are lower limits. And if we couldn't find any data, we just basically skipped the contribution, making even more lower limits here. And then we corrected all the cost data for inflation to 2019 economic conditions. And this gives then a big results table, basically for every infrastructure that we considered, an estimate. And I just want to emphasize again here that these are order of magnitude estimates, because this monetary method that we used, which is a valid method to be used for a carbon footprint analysis, but it has a relatively large associated uncertainty. Typically, it is recommended to use 80%, which means basically you have a factor of 2 up and a factor of 5 down as possible options in your footprint estimate. So we estimate the life cycle footprint, and then we just compute the annual footprint by dividing the life cycle footprint by the mission or observatory lifetime. And if the mission was, or the observatory was started very recently, we divide it by 10 years. so that there isn't a big peak in the annual footprints. Otherwise, it would be a bit an artifact there. So when you then have this big table and you sum up all the numbers, that's basically the sums that you get. So first, interestingly, I mean, for the space missions, we have two completely independent estimates. And they are within roughly 20% at the end, if you sum everything up, which illustrates that the result is quite robust. I mean, here in this cost-based number, there are only 40 missions because there were 6 missions for which we couldn't find any cost numbers. But even correcting for that, I mean, it doesn't make the difference bigger than 20%. So this just illustrates what the typical uncertainty, systematic uncertainty is in these results. And ground-based, we have a lower contribution here, but this is mainly related to the fact that our lab is a space science lab, and we use much more space instruments and ground-based observatories in our lab. So in total, you have roughly 8 million tons of CO2 equivalents over the lifetime of the infrastructures. And if you use the annual footprint, it's roughly 500,000 tons of CO2 per year. Now, we recognize, in fact, that our list, the instruments used by scientists of our lab is in fact quite large. So we can extrapolate these results. We can at least try to extrapolate these results to the world inventory of astronomical research infrastructures. And we did this using a Bootstrap method, which is illustrated here. So we have a list of infrastructures for which we assess the footprint. This gives you at the end this 8 megatons. And then we just bootstrap this list and we say, okay, we know there's a larger number of total infrastructures in total, and we bootstrap from this list. We sample basically our list to get an extrapolation. And this sample is a random sample, so we can just repeat this sampling with a different random number generator seed. And if you do this several times, and we did it 10,000 times, it gives you a nice probability distribution of your sampled infrastructures extrapolated to the world inventory. We also recognize when you do this, sometimes you sample, of course, you sample given infrastructures several times. But some of these infrastructures in our list, I mean, they are so big and have such a big carbon footprint that they don't have really equivalence in the world. Think about the Hubble Space Telescope, which has a very big carbon footprint because of all the servicing missions from the space shuttle and so on. Or think about ALMA, which also has a huge carbon footprint, but these are unique infrastructures. There isn't a second HST or a second ALMA observatory. So if you do this, the sampling, you draw them several times eventually. So we did a modified version of that where we basically fixed the first infrastructure as existing only one time and sampled all the others. And this gives then a lower estimate of the infrastructures. So to also reduce the bias in this extrapolation, so we divided facilities into broad categories like solar physics, plasma physics, astro, optical infrared telescopes, and so on. And then we made the sample in each of these categories. And we determined the total number of facilities that existed in the world in 2019, just by basically collecting data from the web. And also this kind of extrapolation assumes that our 85 facilities are some kind of a representative list of all the infrastructures that exist in the world. So if you play this game, these are the probability distributions that you get. So in blue, you get these are the space missions, and there are 2 histograms. So the filled is for the cost-based estimates. The open is for the mass-based estimates. Here are the ground-based observatories. So their footprint is larger just because there are so much around in the world, much more than space instruments. And the red is then just the sum. So here cost-based sum, and the open histogram, unfilled histogram, the mass-based sum. So this is with the original method, and then when you modify the method by just fixing the most important infrastructure, you get more narrow distributions and lower values. So when you just put these numbers in the table, these are the numbers you get. So typically a footprint around 22 megatons for all infrastructures with the Bootstrap method. The annual footprint goes up to 1,300 kilotons or 1.3 megatons per year. And if you modify this goes a bit down. The modified bootstrapping goes down to basically 1 million megatons per year. So basically you double the footprint compared to the estimate that we just did for the scope of IRAP. Now, the next step we just tried to compare this number by looking in how this number comes out when you divide by the number of astronomers. So we can do this for our lab. We just divide the IRAP footprint by the number of IRAP scientists. This gives 27 tons per year per astronomer. We know that this is probably a lower limit because it turned out in our initial list of 85 instruments, it turned out that there were additional instruments that we didn't catch when we built up this initial list and that are used by astronomers from IRAP, and this will plausibly increase our footprint by roughly 20%. Then when we use the Bootstrap method, it gives a higher value, it gives 43 tons per year per astronomer. But here, take care of sampling unique facilities, and if you avoid this, it goes down to 35 tons. So overall, so we said, okay, taking all these values together, so there's a plausible range of footprints of 37 tons per year with a large uncertainty, and this uncertainty includes the systematic uncertainties due to the method and also the uncertainties in our emission factors and so on. So when you take this number and you think about this, is basically somehow the end result you come up with. When you think about an astronomer, I would say roughly the footprint of an astronomer, a typical astronomer, an average astronomer, is probably around 60 tons per year per astronomer. So I mean, a big part of this is research infrastructures. Then you have all other stuff, your lab, your flying, your conferences, whatever, the purchases of the lab and so on. And of course, an astronomer has also a lifestyle footprint. And if you add this up, this is probably the figure typically you come up with. And whatever target you adopt, I mean, you can argue, and we argued in the paper about a 2 tons emission target per human, or you can argue that you need to downscale emissions by a given factor, 5 or 10, whatever. Or you can argue even on who is responsible for climate breakdown. I mean, these numbers are just all much smaller than this number here. So whatever target is to be adopted, and it's not to us to say which one it is, it will be a fundamental change to how we do astronomy today. Of course, you have to fold in what is the societal impact of astronomy, but also you have to think what are human needs. So what do human need to survive? And what are the human wants? So all the additional stuff in addition to surviving. And then, of course, you have to think about equity and responsibility. Now, this is something that is not really in the paper, but I looked a bit up because, I mean, astronomy is, of course, not the only field that has this issue. I mean, there are other fields intensive in research, intensively using research infrastructures, and they may have the same issue, in fact. And when you look, for example, there is CERN did a carbon footprint analysis, but only the first 2 scopes, scope 1 and scope 2. So only emissions related that basically directly come out of CERN and emissions due to power purchase. And when you just look at the scope 1, which is just emissions coming out of CERN, it's already almost 200 kilotons a year. And this is just all the gases they use to cooling down their detectors. And CERN hasn't made so far a scope 3 analysis, a scope 1 to 3 analysis, but I could imagine that probably it's very close to what the entire astronomy infrastructures account for in terms of carbon footprint. I did another game here. I used just at the S3 list, S3 roadmap, and the S3 divides basically in big science themes. And I just applied our emission factors to the cost values in the S3 roadmap. So here on the left is construction, and here on the right is operations. And I separated because normally astrophysics is in physics. So I separated physics and astrophysics. So if you have physics in total, the thing would be even larger. So you see that physics has the biggest carbon footprint of all sectors in the S3 roadmap, but there are also other sectors that are important. So the message here is, of course, I mean, we now did it for astronomies, but other communities also have to do their homework and estimate what their footprint is in terms of research infrastructures. Now, what you learn when you learn about doing a carbon footprint is that estimating the carbon footprint is, of course, not only the first step, and that a carbon footprint analysis is not complete until you really devise an action plan. And so we said, okay, well, let's also go this step and make a proposal. And that's also what we wrote in our paper about an action plan that we propose based on this research. So we think that the first step is that every plant or existing facility should perform an environmental life cycle analysis. And for the very simple reason, because today very little analysis exists. And of course, you have to consolidate our estimates, which are for the moment only order of magnitude estimates. And then if you need, of course, an informed action plan if you want to reduce your carbon footprint. So you need first to make a life cycle analysis. And also eventually, if you think about implementation, you want to take a decision on should we build this new infrastructure or not, of course, you have to have very solid numbers before making such a decision. And very important also is that these analyses should be made public. And one example could be that the IOU has a register of these footprints. Here I show you an example of an environmental footprint analysis done by ESA. So this covers more than just carbon footprint. Carbon footprint is just the first row, but then you have ozone depletion, material use, water use, and so on. So unfortunately, ESA makes these things since 10 years, but never published an absolute number. So this is very important to make things really public so that people can discuss the outcomes of that. The next step is, of course, carbon footprint reduction, and this applies specifically to everything that exists, so operating of existing observatories, including also space missions, because even if the satellite is gone, you have, of course, operating centers and ground station, which basically still drive your carbon footprint during operations. And a very good example is ESO, and ESO is really showing the way here. At least it's, I guess, the only organization that is very transparent about this. So their current operations footprint is 28 kilotons per year, and they have a plan that they announced recently to save up to 4.4 kilotons a year over the next years. I've no clue over how many years of this, but I'm plausibly. Things need some time to be constructed. It's maybe 5 or 10 years, whatever. And just if you divide one number by the other, you get that this is a 16% reduction in the carbon footprint. So very good. So if people have action plans, they should also be made public, like ESO does it. And again, IAU could be here the reference for that. And then, of course, you have to monitor your action plans and monitor if you follow really with your carbon footprint these action plans. But the real question is, I mean, are these footprint reductions enough? So if you look in this, typically, I mean, I just showed you for ESO the values, it's 16%. And if you see other estimates, typically it's a few 10%. And this compares to a factor of a few that is required over the next decades. I recall that in 2030, we should have divided by a factor of 2 our footprint. And in 2050, we should be basically net zero. And you can, in fact, play some game. And here again, I use ESO, and for the only reason because they are very transparent. So I'm not pointing to ESO. I mean, they are really good in what they are doing. But I mean, if you publish your number, you can just play with these numbers. So the ELT, so the next big optical telescope, optical infrared telescope that is currently under construction, the ESO has an estimate for this footprint, which I guess it's underestimated, but take this number as it is. It's 64 kilotons CO2 equivalents. And if you write this off over 50 years, because I mean, ELT will work for a long time, you would get something like an annual footprint of 1.3 kilotons. Then, of course, as I just said you before, you have a saving of 4.4 kilotons over the next years. So this leaves you 3.1 kilotons left that you can eventually add as additional footprint. But of course, I mean, you need ELT, you have to operate it. And if you just look at the VLT operations footprint, it's already 9.4 kilotons a year today. So it's very likely that just the ELT construction and operation will completely annihilate all the carbon footprint reductions that ESO is putting into place right now. And probably it will not only annihilate, but I mean, the total carbon footprint of ESO will increase at the end. So it's really questionable if you can really achieve the required carbon footprint reductions while still adding new infrastructures at the current pace to your budget. So we came to the conclusion that it's really our strong belief that we need both. We need carbon footprint reductions and a reduction of the pace of deployment of infrastructures. So how can we reduce the pace? And this is also more a personal side note, stuff that I implemented over the last years, specifically using, for example, what's already there. And the obvious example is archival data. And you can always develop new methods and algorithms to analyze this data. There are a lot of archival data that were never analyzed and never explored. So you can do still some mining and get some science out of this data. You can also ask new science questions to old data. I mean, that's what I'm actually doing with students now over the last 2 years. And just the feedback from the students is they say it's a very satisfying exercise, specifically because it's also a low carbon science work, and it's good for their future. And in addition, you can also tackle the more difficult analysis, the ones that you typically don't do because you're always looking for fresh data. It's easier to get low-hanging fruit in fresh data than tackling difficult analysis with old data. And then also you have to use your imagination. I mean, I cannot believe that the way we do science today is the only way how science can be done. And I mean, science was done also different in the past, and sometimes you can learn about this also. And sometimes also new ideas may outweigh new data. So just going mainstream and getting more and more data is maybe not the best way to proceed. And also, at least as a personal reflection, I know I don't think enough about the physics. I'm thinking a lot about the data, but not about the physics. And so I think we can all spend more time to think about the physics to go ahead. And sometimes you have to be unconventional and explore new roads. So actually, there are quite some side benefits in reducing the pace. And this joins a bit the discussions in the slow science movement. So you have more time for reading, more time for discussions, more time for collaborations, and also more time for communication specifically to the general public. And this is very important in a time where fake news are making their way. Another side effect is reduction of publication pressure. And I stumbled over this interesting study very recently. This is just not in astronomy, globally in science, the rise of publications, the growth rate of publications over time. And in red, you see this growth rate, and you see it's really amazing. Over the last 60, 70 years, we have a 5% annual growth rate in science publications. I just looked up these numbers this morning because somebody asked me yesterday when I gave this talk in another forum. Could it be the rise of astronomers? So I looked just up the world population rise, the growth rate over the last decades, and it's between 1 or 2%. So I'm pretty convinced it's not the number of scientists that increased by 5% over the last years. It's really just that people put out more and more publication. And the question is really, I mean, how and if this curve can continue. And finally, of course, if you put more money in slow science, and if you put less money, in research infrastructures, there's more money available for decarbonizing existing infrastructures. So to conclude, we believe that the solution is in fact in our hands, and so the only question is, I think, whether the astronomical community will choose to recognize it and make use of it. And probably now the discussions that we have will already show if we can go in this direction. Okay, thanks a lot. I think I leave the slides like that, and I'm open for your questions.